Hi, everyone. Thanks for showing up for the second installation of my journey into resting metabolic rate. So in the last video, we talked about resting metabolic rate, what it was, why it is, and some background behind it. But in this video, I'm doing my favorite thing ever, which is mathematics. So we're calculating resting metabolic rate using one, predictive equations, and two, data from an indirect calorimetry protocol. So we're going to start with I guess what can be considered the hardest thing, and then going on to the things that are easier, which are the predictive equations. And I would like to double check and see if I'm recording. We are recording. Perfect. All right, back to it. So, and during an indirect calorimetry protocol, a participant lies out on a bed in a supine position, and they are covered with a hood, a plexiglass hood. They are stuffed in pretty tight using like a blanket and the flaps around the hood to make sure no air gets lost. We want to keep it all within the hood and connect it to the computer eventually. So we connect the hood to the metabolic cart, and from here we measure VO2 and VCO2 continuously, which is the volume of oxygen and the volume of carbon dioxide. So a total test lasts 30 to 45 minutes, and the job the participant has is to stay as still as possible without sleeping. And I can tell you right now that that is super difficult. So the total test, 30 to 45 minutes, but the first 10 to 15 minutes are used to reach metabolic steady state. So basically that means the participant is getting used to being under the hood and the computer is getting used to having the participant being measured. From there, we use the final 15 to 30 minutes, and that's for data collection. So output of importance during this test includes the respiratory quotient. The respiratory quotient is used to indicate substrate utilization, which is the ratio of carbohydrates and fats that you use doing a test like this. And we also use it to help us find the calories connected to each liter of oxygen consumed. So, usually during a rested metabolic test, you're burning more fats than carbs. And during a test like this, we can expect to see a respiratory quotient between 0.7 and 1.0. Maybe asking, how does this make sense? To make it all make sense, we're going to actually create the ratio. So, respiratory quotient is the amount of carbon dioxide produced over the amount of oxygen consumed. During a resting metabolic test, this ratio should equal less than 1. So, for example, if the carbon dioxide produced on average during a test is 250 milliliters per minute, and the oxygen consumed is 350 milliliters per minute, we are going to get an equation set up of 250 divided by 350, hugging as tightly as possible to the units. Milliliters per minute are going to cancel out across the board. And let's see here. I'm going to calculate this using a calculator for verification. 250 divided by 350 is going to be 0.71. So the closer a value is to 0.7, the higher the amount or the contribution of fats to this equation or to resting energy expenditure overall. So respiratory quotient of 0.71 is going to hang out right here. So at this ratio, we're burning almost 100% fats, and that can make more sense in another video. So this metabolic test report is just an example of what the results of an indirect calorimetry protocol looks like. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9 variables that we could talk about. But in this video, I just want to focus on VO2, VCO2, and respiratory quotient. And this is tracked from minute 1 all the way to minute 45. And we can take values, and these aren't the answers or the averages from the test. I just wanted to show you an example to make it all make sense or more sense. So from here, using this example, we're going to calculate resting metabolic rate. And as you can see in this particular slide, we actually get an answer for resting energy expenditure or resting metabolic rate. But in order to like appreciate the values, we need to back up and figure out how the protocol or how the system gets to the resting energy expenditure slash resting metabolic rate value. So in here, we have these variables, a VO2 average of 300 milliliters per minute across a test, and then an average VCO2 of 265 milliliters per minute. Now, I made these variables up, and so we'll just walk through this example. It's simply an example. So, first things first, as you can tell, we don't have a respiratory quotient. We need a respiratory quotient before we can get calories per day, and so on and so forth. So the only units we have right now are milliliters per minute. At the end of this slide in particular, we need a number connected to the units kcals per day, because RMR is expressed in kcals per day. So this is our goal, and I'm going to walk through the path to get to that goal. So you remember, to determine respiratory quotient, we're going to divide our VCO2, which is 265 milliliters per minute, by our VO2, which is 300 milliliters per minute. And we're going to track these units like a hawk. So those cancel. 265 divided by 300 is 0.883333, and we're going to round that to 0.88 so we can actually use it. So that is our RQ. And so next step is to use that respiratory quotient to determine the amount of calories this person is burning per liter of oxygen they're consuming. And we're going to use table 13. Now, table 13 has been used for hundreds of years to calculate the amount of calories burned per liter of oxygen. So we're going to use it here as well in 2026. So this column here is the respiratory quotient. And this is the number of importance that we're going to gather when we connect this to this. So calories per liter of oxygen. We have a lot of other columns here that we could talk about. So if you have any questions or you want more insight into that, just leave a comment and I'll be happy to like talk about that because I love talking about numbers and exercise science. So from here, if we have a respiratory quotient of 0.88, we're going to go down to 0.88 here. And right beside it, we can see the calories burned per liter of oxygen, and that is 4.9. Zooming in, you can tell that it is a blurry 4.900. So with a respiratory quotient of 0.88, this person is burning 4.9 kcals per liter of oxygen. So we've moved a little bit. We have that kcals or calories that we're going to use in the final answer, but we don't have day. So how are we going to get from kcals per liter to kcals per day? We're going to do that in the next step. So we no longer need our respiratory quotient or our VCO2. We're going to say bye to that. What we do need is our VO2. So VO2 is 300 milliliters per minute. We've got to somehow connect that to 4.9 kcals per liter. In this situation, we're going to multiply these together, but first we're going to convert milliliters to liters. So VO2 milliliters per minute, we can simply divide that by 1,000. Nope, milliliters per minute. This is going to cancel because they are the same. Oh, that's milliliters per liter. Every 1,000 milliliters is a liter. I don't know why I put minute. But anyways, those are going to cancel, and we're going to get 0.3 liters per minute. All right, so from here, we're going to multiply 0.3 liters per minute by 4.9 kcals per liter. We're one step closer. So the liters are going to cancel, and we're going to multiply 4.9 by 0.3, and that's going to be step number 4 equals 1.47 calories or kilocalories per minute. So we're an inch closer. We still have kilocalories like we're going to have in the final answer, but we need to get from kilocalories per minute to kilocalories per day. And the significance of this is that when you're doing absolutely nothing, you're going to burn calories. And in my opinion, that's a substantial number of calories for doing nothing. So, step 5, the final answer. To get from kcals per minute to kcals per day, we're going to multiply 1.47 kcals per minute, whoops, by 1440 minutes per day. And you may be asking, how did I get that number? You multiply 24 hours by 60 minutes, and you end up with 1440 minutes per day. So, anyways, the answer is going to be 2,116.8 kilocalories per day because the minutes cancel. This is our final answer. And you can actually just round it up to 2,117 kilocalories per day. So hopefully that gives you a better appreciation for what it takes to do a test like this and get the results that we do. So next, we're going to go over a particular predictive equation. The Rise-Harris-Benedict equation, slightly different equations for men and women, and I want to walk through, just for significance, how to answer each one. What you'll notice is we will not be holding the units as we walk through the test. This is just showing us where to drop the units, or so weight in kilograms, centimeters, and age. So I was going to use this slide to write out each example. So next up, but since we already have the equations here, I'm just going to write it out here and answer it. So for men, or this particular man, we're going to start with that constant of 88.362 plus 13.397 times kilograms, which is 90, plus 4.799 centimeters, which is 188, and then minus 5.677 times his age. Now, this is a place where I easily trip up, and that is with the final subtraction. So make sure you keep an eye on all of the signs. Like, I'm more likely to add this value than subtract it. So if you're struggling with a particular sign, definitely circle it so you have your eye on it. But anyways, so we still have 88.362. Keep an eye on all your numbers. 13.397 times 90 is 1,205.73. 4.799 times 188 is 902.212. And in all honesty, I almost added a plus just now. So 5.677 times 25 is 141.925. So we're going to add and subtract. Please hold while I add all these together. Plus 1205 plus 0.73 plus 902.212. 925. And make sure you check your numbers before you submit them anywhere. So when we add and subtract all these together, the final boss answer is 2054.379, according to my calculations. You can definitely check me if needed. So we can also just convert this to a whole number of 2054. And then our unit is going to be kcals per day. So like I said before, this is a predictive equation. It will not have units because we used the values. They used kilograms, average kilograms, centimeters, and H to create the predictive equation. So you don't have to see it or like convert it to kcals per day when it's all said and done. All right. So for women, same process. 4.47693. Monitor your numbers. And like I said before, I'm going to circle where I would be tripped up easily. So 447.693 plus 927, no, 9247 times 75, slightly smaller than the guy, 3.098 times 170 centimeters minus 4.330 times 35. And again, in the last video, talked about the older you get, the lower your resting metabolic rate. And that's just because you can see that in predictive equations. So if this lady was 25, her resting metabolic rate would be higher than it is at 35. And honestly, regardless of the person, because you can see that same trend for the equation specifically for men. So continuing to walk forward, keep track of your numbers. Plus 247. And I'm using a calculator just to have complete confidence in my answers. So 693.525 times 170. And again, even though I have the unit there, we're not going to carry it over. And then that's 526.66 minus 4.330 times 35, which is 151.55. And again, we're walking through these equations just so you see the significance. So 0.693 plus 693.525 plus 526.66 minus 151.55. And we get, and let me track all my numbers, 525.66, and okay. So we should have a value of 1,516.328. And make sure you check your math, and you can check my math too. And that ends up just being 1,516 kcals per day. So those are the final boss answers. Now, the last thing we're going to do is calculate resting energy expenditure, also known again as RMR, using Mifflin St. Jeor. We're going to compare our answer to the one we got during the Harris-Benedict equation. And this example is for the same guy using the same values shown here. And I will carry over the answer from that particular example. So 2,054 kcals per day. HB. So from here, let's go ahead and answer this question or walk through the calculations. 99.99 times 90 kilograms plus 6.25 times 188 centimeters minus, and again, I need to remember the minus, minus 4.92 times age plus 166 times 1 because he is a man. 9.99 times 90 is 899.1. 6.25 times 188 is 1,175 minus 4.92 times 25, which is 1, 2, 3. And again, I need to keep my eye on this subtraction. And then 166 times 1 is just 166. So let's go ahead and add all these together. 899 plus 1.1 is that. 75 minus 1, 2, 3 plus Six. Final answer is 2,117.1, which rounds down to 2,117 kcals per day. So this is almost 60 calories higher than the Harris-Benedict equation. I'm just going to write that right here. So not too far off. Kcals per day. And I would have put the calculations here, but I did not. So hopefully you gain even more appreciation for resting metabolic rate and how we calculate it. If you have any questions, please drop them in the comment. And thank you for listening and following along.